Welcome back to Talk Tensors. We love breaking down the latest and greatest in machine learning research, and today we're diving deep into a paper that's really been making waves
Yeah,
in the world of diffusion models.
it's called.
It's called From Discrete Time Policies to Continuous Time Diffusion Samplers, Asymptotic Equivalences, and Faster Training.
Yeah, don't let the title
I know, right?
intimidate you.
Yeah,
We're going to unpack it all.
we're here to break it down.
It's a fascinating paper. It really gets to the heart of how we train diffusion models, especially when we only have information about the energy function of a distribution and not the distribution itself.
Right?
And this is a common scenario in many fields like physics or finance,
Yeah, for sure.
where we might know the energy landscape, but obtaining actual samples is incredibly difficult.
Right, exactly. And that's where diffusion models come in.
Yeah.
Imagine you're looking at, a perfect photo and someone starts adding noise to it little by little until it's just a mess of random pixels.
Right.
A diffusion model learns to reverse that process,
Exactly.
starting with the noise and gradually removing it to generate a brand new image.
Exactly. And this paper explores a clever way to train these diffusion models without needing samples from that target distribution,
Okay,
which is a big deal.
that's huge.
Plus, it unveils a surprising connection between discrete time policies like those used in reinforcement learning
Oh, wow.
and the continuous time processes that drive diffusion models.
Okay, I am intrigued. So for our listeners who might be new to diffusion models, can you give us just like a quick overview of why they've become such a big deal in machine learning?
Well, diffusion models have really taken off because they excel at generating high-quality samples from complex distributions. Think about creating realistic images or composing music or even designing new molecules.
Wow.
These models can learn the underlying structure of the data and then use that knowledge to generate new samples that look and feel authentic.
That's amazing. But as you mentioned, training these models traditionally requires tons of data samples, which aren't always available.
Right.
That's where this paper's focus on training without samples comes in.
Absolutely. This paper dives into the theoretical connections between discrete time methods and their continuous time counterparts, and it uses mathematical proofs to show that as you make those time steps in a discrete model smaller and smaller, the training objectives actually converge to the continuous time equivalence. This is a pretty profound finding because it suggests we can achieve similar performance with coarser time steps, which means faster and more efficient training.
Wow. Now, you mentioned something about reinforcement learning and G-flow nets earlier.
Right.
How do those fit into this whole picture?
So traditionally, if you wanted to sample from a complex distribution, you would have had to rely on methods like Monte Carlo simulations or deep generative models.
Right.
They work, but they have their limitations.
Sure.
That's where neural stochastic differential equations or neural SDEs come into play. They provide a powerful way to model generation as the reverse of a diffusion process.
Neural SDEs. That sounds pretty complex.
Think of it like this. We start with a simple distribution, like a bell curve, and then use a neural network to gradually transform it, guided by an SDE, until it resembles our target distribution. It's like sculpting something intricate from a simple lump of clay.
Okay, I think I'm starting to get the picture. So how do we actually train these neural SDEs for sampling?
There are two main methods.
Okay.
Differentiable simulation, where you train by differentiating through the entire simulation process of the SDE,
Okay.
and off-policy reinforcement learning, where you learn from a set of pre-generated trajectories. Each method has its advantages and disadvantages.
And this is where the paper starts bridging the gap between these approaches, right? By connecting discrete time policies used in reinforcement learning with the continuous time processes in neural SDEs.
Exactly. They show that these two worlds, which seemed quite separate, are actually deeply connected. And what's really exciting is that by leveraging these connections, we might be able to achieve similar or even better performance by training with coarser time steps. This could significantly speed up the training process, especially for complex, high-dimensional problems.
So how does this paper actually show this connection? Like, what kind of methods did they use?
Well, they start by introducing this concept of path measures. It's a way to represent the distribution of trajectories, both in discrete and continuous time. And then they prove that the training objectives used in discrete time settings actually converge to objectives that minimize the difference between these path measures in continuous time as those time steps shrink.
Okay, so they're basically showing that as we make the time step smaller in a discrete time model, it gets closer and closer to a continuous time model in terms of what it's trying to optimize.
Precisely. And they use a neat mathematical tool called Euler-Maruyama discretization to bridge that gap. It's a way to approximate a continuous time process using discrete time steps.
This is where G-flow nets really come into the picture, right? You mentioned them earlier.
Yes, G-flow nets are a fascinating framework for learning probabilistic models inspired by the flow networks you see in, say, fluid dynamics. They provide an elegant way to learn complex distributions, especially when we only have access to the energy function.
So how do these G-flow nets connect to the continuous time diffusion processes we've been talking about?
One of the key ideas behind G-flow nets is this concept of detailed balance. It's a local constraint that ensures a kind of equilibrium in the flow of probability within the network. And what's really amazing is that the paper proves that these detailed balance constraints actually approach the partial differential equations, specifically the Fokker-Planck equations that govern how the SDE's marginal densities evolve as time steps get infinitesimally small.
Wait, so those detailed balance constraints in the discrete time G-flow net are like a mirror image of the equations that describe the continuous time diffusion process. That's pretty mind-blowing.
It is, and this connection has practical implications too. It suggests we can train diffusion models more efficiently by working with coarser time discretizations, potentially leading to faster training times and better sample efficiency.
Okay, so they have all this theory, but did they actually put it to the test? Do they run any experiments to see how well this all works in practice?
They absolutely did. The paper includes a series of experiments where they evaluate the effects of different time discretizations on training diffusion models. They test a variety of objectives, including the path integral sampler trajectory balance Vargrad, and of course the detailed balance objective inspired by G-flow nets. They even try it with and without a clever trick called the Langevin parametrization, which incorporates the energy gradient into the drift term of the SDE.
So they really covered their bases. What kinds of target distributions did they test these methods on?
They use a diverse set of target distributions, ranging from simple mixtures of Gaussian distributions to more complex high-dimensional energy landscapes, which are more representative of the challenges we see in real-world applications. They wanted to make sure these ideas worked across a range of scenarios.
And drumroll, please. What were the results? Did training with coarser time steps actually lead to faster training and better performance?
The results were incredibly promising. They found that training with coarser, non-uniform time discretizations often outperformed training with uniformly spaced time steps, particularly when using fewer steps.
So less is more in a way. That's a pretty significant finding.
Yes, and they observed not only faster training times, but also improvements in sample efficiency, meaning they could achieve good performance with fewer training samples. This is a huge win, especially when dealing with data sets where obtaining large numbers of samples can be costly or time-consuming.
This all sounds really groundbreaking. But before we jump into the novel notions section and discuss potential extensions of this work, I want to make sure our listeners understand the key takeaway here. Can you summarize it for us?
The core takeaway is that this paper reveals a deep connection between discrete time policies like those used in G-flow nets and continuous time diffusion samplers. This connection suggests we can train diffusion models more efficiently by using coarser, non-uniform time discretizations, leading to faster training times and better sample efficiency. And their experiments back this up.
Perfect. Now let's dive into the really exciting part. What are some potential extensions of this work? What novel notions are you thinking about?
Well, one of the most interesting possibilities is using these ideas to tackle high-dimensional problems which are common in fields like computational biology and astrophysics. In these domains, the length of the trajectories we need to simulate can be a major computational bottleneck. Reducing the number of time steps required for training could be a game changer.
It's like we're compressing time itself, allowing us to explore these vast, high-dimensional spaces more efficiently. What other avenues do you see opening up?
This research could also inspire new algorithms and theoretical frameworks that generalize these results to even more complex scenarios. For example, we could explore diffusion processes on manifolds, which are curved spaces, or even delve into the world of non-Markovian processes where the future state depends not just on the present, but also on the entire history of the system.
That sounds incredibly complex. What kind of impact could these generalizations have on the field of machine learning?
Well, they could revolutionize how we approach a wide range of problems, from drug discovery and material science to climate modeling and financial forecasting. Imagine being able to efficiently sample from extremely complex, high-dimensional distributions that were previously intractable. The possibilities are truly mind-boggling.
It's like unlocking a whole new level of understanding and control over these intricate systems. But as we delve deeper into these complex scenarios, are there any potential challenges or limitations we need to be aware of?
That's a great question. One challenge is that as we move to more complex scenarios like diffusion on manifolds or non-Markovian processes, the mathematical tools and theoretical frameworks we rely on might need to be adapted or extended. We might need to develop new techniques to handle the increased complexity.
So it's not just a matter of plugging in these ideas and expecting everything to work perfectly. It requires careful thought and further research to make sure these methods are robust and applicable to these more intricate settings.
Exactly. Another potential challenge is computational complexity. Even though we're aiming for more efficient training with coarser time steps, dealing with extremely high-dimensional spaces or long-range temporal dependencies can still be computationally demanding. We might need to explore new algorithms and hardware architectures to handle those challenges effectively.
That makes sense. It's like we're constantly pushing the boundaries of what's possible, and as we do that, we encounter new computational hurdles that we need to overcome.
Precisely. But I'm optimistic about the future. The field of machine learning is incredibly dynamic, and researchers are constantly developing new techniques and tools to address these challenges.
So as we wrap up our deep dive into this paper, what are your final thoughts? What key takeaways would you like our listeners to remember?
I think the most exciting aspect of this paper is the bridge it builds between discrete time policies and continuous time diffusion processes. This connection opens up new possibilities for training diffusion models more efficiently and effectively. The idea of using coarser, non-uniform time discretizations is particularly intriguing as it could lead to significant speedups and improve sample efficiency.
Absolutely. And the potential applications are vast, spanning fields like computational biology, astrophysics, drug discovery, and so much more.
It's a testament to the power of theoretical insights in driving practical advancements in machine learning. This research is a great example of how understanding the fundamental connections between different areas can unlock new possibilities and lead to groundbreaking innovations.
And to our listeners, we encourage you to delve deeper into this paper and explore the exciting world of diffusion models. Who knows, maybe you'll be the one to come up with the next big breakthrough.
Until next time, keep those tensors talking.